Hi, my name is Henri Gode and I welcome you to my EUSIPCO 2022 presentation, which is titled Adaptive Dereverberation, Noise and Interfere Reduction using Sparse Weighted Linearly Constrained Minimum Power Beamforming. So let's first go through the outline of this talk. We'll start with a problem statement, that is multi-microphone speech enhancement for spatially non-stationary scenes. Instead of more traditional cascaded systems performing dereverberation and noise and interference reduction successively, in this work we consider the weighted linearly constrained minimum power beamformer, in short wl.CMP, which performs dereverberation, noise and interference reduction jointly. Since wl.CMP is a non-adaptive algorithm, it is unable to adapt to spatially changing acoustic scenes. So we proposed an adaptive version of the wl.CMP. In the evaluation, we compare the performance of the proposed adaptive wl.CMP beamformer with its non-adaptive version for a scenario with a sudden switch of target speaker position. And finally, we conclude the talk and provide a brief outlook. So, assuming we are in a scenario with a microphone array, could be for example hearing aids worn by a listener, which captures reverberant signals from a potentially moving target speaker and stationary interfering source and diffuse background noise resulting in our noisy signal. Note that we assume all sources and the noise to be uncorrelated. In the STFT domain, we denote the noisy microphone signals by YT, whereby T is the frame index and the frequency index is omitted for ease of notation. The target signal and the interfering signal are denoted by X1T and X2T respectively. The reverberant signals of the target speaker and the interfering source can each be separated into their direct path plus early reflections denoted by D and their late reverberation denoted by R. And the noise is denoted by NT. So the goal of multi-microphone speech enhancement is now to extract the direct path plus early reflections, so D1T, from the noisy reverberant mixture. In the following we will call D1T the desired target signal. So now I will briefly introduce conventional non-adaptive methods which aim at extracting this desired target signal in case when nothing is moving. The first method is called the linearly constrained minimum power beamformer, in short LCMP, which aims at interference and noise reduction. The LCMP beamformer is applied to the current time frame, so it is a single frame method. The optimal filter is found by minimizing the output signal power, subject to linear constraints using the relative transfer functions of the target and the interfering source, and it has a closed form solution. The weighted prediction error method, in short WPE, aims at dereverberation using a multi-frame filter applied to past frames to estimate the reverb and subtract it. The WPE filter is optimized, maximizing a likelihood function based on a time-varying Gaussian model, in short TVG, for the desired target signal. Since WPE has no closed form solution, it has been shown to use an iterative alternating scheme. Then it was proposed to combine these two approaches into the weighted linearly constrained minimum power beamformer, in short wl.CMP, to perform joint dereverberation, noise and interference reduction. So this wl.CMP beamformer is derived by specifying the signal model so that each reverberant source signal is approximated by a convolution over time frames of the clean speech S with a respective convolutive transfer function denoted by A. You can see that the convolution is divided into a term corresponding to the direct and early signal components, DT, and a term corresponding to the late reverberant signal components, R. The separation is done by the so-called prediction delay tau. You can see this here and here in orange. Now, to give an estimate of the desired target signal, the wl.CMP filter H bar is applied to a stacked multi-frame signal vector y bar containing the current frame yt and some past frames. Note that the filter is not applied to the tau most recent frames, so there's a gap in the stacked signal vector seen by this orange line here. And if you look here, there's another representation of this signal vector which contains all the blue frames, but the white frames correspond to the gap of the tau-1 most recent frames. Now it has been proposed to optimize the filter H-bar by modeling the desired target signal with a time-varying Gaussian, resulting in this cost function. So time-varying Gaussian means that the variances are independent over all time frames and are given by the power of the desired target signal, as seen here. But this cost function is not complete yet, because additional linear constraints are formulated using the relative transfer function vectors of the sources contained within the matrix C-bar. Here you can see a green 1 corresponding to a distortionness constraint for the target source, and the beta in red denotes a gain reducing the interfering source. These RTF constraints also have the effect that the binaural cues of the sources are preserved. Unfortunately, there's no analytic solution to this optimization problem, so that it was shown to use an iterative optimization scheme with 2 alternating steps. So in one step the variance is updated, which are then used in the next step to compute or update the filter H-bar. In this filter update you can see the covariance matrix RY lambda of the current and past frames, which is available in general. However, one also needs the relative transfer functions of the sources in C-bar, for which it is far from trivial to estimate them from the noisy mixture, but this will be discussed later. So for now we have seen the non-adaptive wl.CMP beamformer, which is nice because it handles dereverberation, noise and interference reduction jointly, in contrast to the LCMP beamformer and WPE dereverberation. However, we want to be able to extract a moving target source from the noisy mixture, and the problem is that non-adaptive methods are not able to adjust to spatial changes in the acoustic scene. Therefore, we want to propose an adaptive version of the wl.CMP beamformer. So here we can see an important change in the filter operation, namely that our filter H-bar is now time dependent, denoted by the subscript T. And here we have again our non-adaptive cost function, which we need to change somehow in order to find an optimal filter, not for a time batch, but for each time frame T. So therefore, this adaptive cost function, you can see that the filter H-bar and also the matrix containing the relative transfer functions C-bar are time dependent now. They have the index T. And additionally, we incorporated an exponential window weighing the most recent frames a lot more than the distant past frames. The forgetting factor gamma defines the smoothing constant of this exponential window. Okay, so in the difference between these two cost functions, you see the key point of adaptive wl.CMP. However, in a second step, we generalized the adaptive cost function using sparse priors, similarly to an existing WPE variant. This introduces the shape parameter P, which can be used to adjust the amount of sparsity promoted by the cost function. So this will be our final cost function we want to solve. Again, there's no analytic solution, so we use an iterative optimization scheme very similar to the non-adaptive version. The variance update changed slightly by subtracting the shape parameter P in the exponent. So for P equals 0, it is equal to the conventional variance update. And the filter update now uses a moving average of the noisy covariance matrix R bar and time-dependent relative transfer function vectors in C bar. So to compare the proposed adaptive wl.CMP beamformer with its non-adaptive version, we simulated left and right behind the ear hearing aids, each having 2 microphones in a room with a reverberation time of T60 equal to roughly 510 milliseconds. Recorded diffuse babble noise was always active with an SNR of 0 dB, And using measured room impulse responses, we simulated a stationary interfering speaker at -120° direction of arrival, which starts talking after about 1 second. Simulated in the same way, a male target speaker starts talking after 2 seconds at 0° direction of arrival. And it is superseded after 20 seconds by a new female target speaker at 90° direction of arrival. So this switch of target and position also means that there's a new relative transfer function of the target source, and we aim to adapt to these changes. So here you can see the fixed parameters of the algorithm. The signals were simulated at 16 kHz, and the STFT framework used frames of 32 millisecond length and 50% overlap. The filter length was set to 16, corresponding to 256 milliseconds, and the prediction delay tau was set to 3 in order to keep the early reflections. The interferer gain was -20 dB, and we used only one iteration to save computational costs, since preliminary results showed reasonable convergence after the first iteration. So since we are interested in adaptation, we evaluated various smoothing constants, and since we introduced the shape parameter p, we also evaluated for 2 different p-values. As mentioned before, it is far from trivial to estimate the relative transfer function vectors of the source. So for now, we used the noise and undesired covariance matrix to estimate the interfering relative transfer function vectors, and the undesired and noisy covariance matrices for adaptively tracking the target relative transfer function vectors. Estimates of these necessary covariance matrices are computed from corresponding periods of the signal, which we assume to know oracally. As objective measures, we evaluated the improvement of the frequency-weighted segmental signal-to-noise ratio, in short, frequency-weighted SSNR, and the improvement of the signal-to-reverberation ratio, in short, SRR, both averaged over left and right ears and using the desired target signal as reference. Here you see the frequency-weighted SSNR and SRR improvement compared to the noisy input signal of the non-adaptive wl.CMP beamformer. And it is positive, which is nice. This green curve shows the performance of the adaptive wl.CMP beamformer using different smoothing constants T gamma. This results use the conventional variance update with p equals 0. Here now you see the corresponding results when adjusting the shape parameter to p equals 0.5. Now we can say that all versions of the wl.CMP beamformer improve frequency-weighted SSNR and SRR. And as expected, the adaptive wl.CMP beamformer clearly outperforms its non-adaptive version. However, adjusting the shape parameter to 0.5 only yields a small benefit in terms of SRR compared to p equals 0. And we see that smoothing constants between 200 and 500 milliseconds yield the best performance in the given scenario. So to conclude, in this work we proposed an adaptive sparse wl.CMP beamformer for joint dereverberation, noise and interference reduction, which is capable of enhancing a moving target source. And the generalization using sparse priors, which introduced the shape parameter p, was seen to have only a minor effect. So most importantly, our proposed wl.CMP beamformer outperforms the non-adaptive wl.CMP beamformer, which can be explained partly by its ability to track time-varying RTF vectors of the target speaker. So as a brief outlook, in future work we look at successive RTF vector estimation for multiple sources from which this wl.CMP beamformer could benefit. And now I want to thank you for listening to my talk, and if you have any question or comment, feel free to contact me via email. Bye!